Okay, so now that we have an idea of how to write equilibrium expressions and how to essentially just do the math, plugging the numbers in for the concentrations of the products and reactants at equilibrium raised to their respective stoichiometric coefficients. Now what we're going to do is we're going to actually calculate equilibrium concentrations and calculate Kc values and also the reaction quotient values at different time points, and we're going to compare them, the QC and the Kc values, in order to predict the direction that a reaction is going to proceed in. And what we're going to be using to predict the direction of a reaction is we're going to compare reaction quotient, which is our QC. This is the value at any time point. When we write the law of mass action relationship in the reaction, we're going to compare this value to the value Kc, and this is at equilibrium. Okay, so there are going to be three possibilities that we're going to come across when we compare Kc to the QC, the reaction quotient, right? Let's just write that on here. This is the reaction, which is just a general way that we represent the relationship between the products and the reactants. And then Kc is a specific case of QC, the reaction quotient. This is under equilibrium conditions. So if we find that Q, the reaction quotient at any point in time in the reaction, is actually less than K, right, what this means then is the ratio of the concentration of the products or reactants is small. And in order to reach equilibrium, the reactants have to be converted to products. And what this means then as a system is you're going to proceed in the forward direction. In other words, if you remember, the forward direction means to the products. So the reaction then will proceed from left to right to the product side. Okay, so what this essentially is saying is if Q is less than K, that means the reaction quotient QC has a smaller value than K. In order to get to K to establish equilibrium, we have to go from left to right to make the concentration of the products greater than what they are at point QC. Now remember, that expression is the products raised to a particular power, which is the coefficient, divided by the reactants raised to their coefficient as well. If Q is equal to K, then that means the system is at equilibrium and the reaction is not going to proceed in any one direction. Okay, so the reaction will not proceed in any direction, left or right, towards the products or reactants towards the forward direction or the reverse reaction, because we are already at equilibrium. And the third possibility, if the Q value at time point is greater than K, if Q is greater than the equilibrium value, that means then that at Q our product is greater than the reactants. That means then what we need to do in order to get to equilibrium, that products need to be converted back to the reactants. The equilibrium then, or the system, will proceed in the reverse direction. Okay, so to the reactant side. And that means then from the right to the left. In order then to get us back to that equilibrium, but get us down to that equilibrium value. So these are the situations we're going to come across. Okay, and when we calculate QC, we're going to just compare it to the Kc value to predict how the system is going to proceed. Is it at equilibrium if Q is equal to K? Is Q less than K? That means the system is going to proceed in the forward direction to the product side, left to right. If Q is greater than K, that means we have a greater amount of the products than we do at equilibrium. So the equilibrium then of the system is going to proceed in the reverse direction to reduce the concentration of those products to get us back to equilibrium. All right, so now we're going to take a look at how we can calculate equilibrium concentrations in a system, and we can calculate these equilibrium concentrations if we know the equilibrium constant, then all this becomes is just a math problem. And as you probably have seen in all the examples we've done so far, that's the common thread, right? It's just math problems applied to chemistry is really what we're doing. So let's take a look at a simple example here. We have this molecule on the left called cis-stilbene. You will learn more about cis and trans isomers when you get to organic chemistry. This cis-stilbene can convert into its other isomer, its other form called trans-stilbene. And this is equilibrium, it's a reversible reaction. And we're told that the Kc value for this at 200 degrees Celsius is 24.0. We can write the Kc expression for this, right, which is the products over the reactant. So we have the concentration of the trans isomer raised to its coefficient, which is 1. We can omit the 1 just for simplicity's sake. And we're going to divide that by the concentration of the cis-stilbene raised to its coefficient, which is also 1. We can omit that for simplicity's sake. And we're told that this is equal to 24.0. Okay, so let's say that we're given a situation where the initial concentration of the cis-stilbene is 0.850 molar, then what we can start to construct is what's known as an ice table. Okay, and this ice table will allow us to determine or to calculate different concentration values that we can then use to determine our equilibrium constant if we needed to do that, or we can find any of the other unknowns. So the I here stands for initial. That's the I. The C stands for change in concentration. So this is initial concentration. This is change in concentration. And then the E here, as you can probably guess, stands for equilibrium concentration. Okay, so at the beginning in our example, we have 0.850 molar. At the beginning, we don't have any of the trans-stilbene because all we're doing is we're starting with the left side, the reactant side. So as this reaction proceeds, we can do a little bit of, we can apply a little bit of math to this. So according to the stoichiometry of this equation, everything is in a 1-to-1 ratio. So as this reaction proceeds, we're going to then experience a change in the concentration. And the change here is simply plus X. All right, so we're gonna have 0 of the trans-stilbene to start with. After we have established equilibrium, we're going to gain a certain amount of the trans-stilbene. We're just going to call this X for right now. And because we're making it, we have the positive sign. Well, guess what? According to this stoichiometry, if we gain X amount of trans-stilbene, that means you have to lose X amount of the cis-stilbene because everything is in a 1-to-1 mole ratio. And because we're losing it, we have that negative sign. So to get the equilibrium concentration, all we're doing is we're taking the initial and we're addressing that change that's happening. So in the case of the trans-stilbene, right, we have the 0 that we started with 0 molar, and then according to the change in the concentration, we're going to add X to it. So 0 plus X gives us X. For the change in the cis-stilbene, we started off with 0.850 molar, and then we're losing X amount of the cis-stilbene. So the change there is 0.850 minus X, right? So now we're using a little bit of algebra in this, and now we can take these values, these equilibrium concentrations, and we can now substitute them into our expression for Kc. So now we know that our Kc is equal to the concentration of the trans-stilbene, which is X, divided by the concentration of the cis-stilbene, which we now know is 0.850 minus X. We'll put that in parentheses. And when we evaluate this, we end up with 24.0. Okay, so this then again just becomes math equation. We've defined the equilibrium concentrations in terms of this unknown X. And we can simplify this. So let's say now x over 0.850 minus x is equal to 24.0. So rearranging our equation, right, we have x is equal to 24.0 times 0.850 minus x. And then what we can do is we can isolate x on one side of the of the equation. So my calculator over here. So let's evaluate this really quick. So we have now x is equal to, and we have 24.0 times 0.850. 24.0 times 850 is going to give us 20.4 minus 24.0x, right? So we just multiply out in this. We isolate x on the x terms on one side. So x plus 24.0x is equal to 20.4. So this then will give us so x plus 24x will give us 25.0x is equal to 20.4. And we just solve for x then. So x will be equal to 20.4 divided by 25.0, and that is going to be equal to 0.816 molar. So we found what x was. Now what we can do is go ahead and substitute these back into our equilibrium concentrations, which we defined as x. So in the second table here, what we're doing is we're just substituting what x is. All right, so in the case of the trans bean, remember this was plus x, so x here is 0.816, and here it was minus x. Again, x was 0.816, so we just subtract these, we add it here, and we end up with our equilibrium concentrations. All right, so this ends up being 0.034 molar, and then this here ends up just being the same thing because we just gained that amount. All right, so we're able to now calculate the equilibrium concentrations of both the reactants and the product just by applying a little bit of algebra to this problem, this chemical problem, and doing the math on it.